Hey guys, how's it going? So today we're going to be climbing the Mount Everest or Olympus Mons, whatever you think is cooler. I think Olympus Mons is slightly cooler 'cause it's a volcano. But we're going to be climbing this metaphor of mathematics and physics, right? This terrain, if you will. So I actually forked this kind of starting point from the sheafification and the Portal Wiki. So go ahead and go check those out. They are really good reads, and kind of establish, I guess, the most direct line or path to get to the top. So that's basically what we're doing here, and I've just added my own little, types of books that I think are good contributions to the list, and I also split it across three different routes. So but yeah, so this is what we're gonna call this base camp here, and I like this picture; it's kind of cool. And then this is a picture of Olympus Mons from space. So yeah, I think it's pretty neat. Um, you're basically gonna want to first have some like basic mathematical language and proof techniques before you climb the mountain. You're gonna want to be fluent with sets, logic, induction, epsilon, delta, text right here. Um, you'll want to you really want to focus on calculus. I mean, the basic mathematics you could probably read this in like 4 hours. I have it right here with me. Pretty good. More of like a high school book, but it's a really good reference for and it's really good writing too. Just in case like I keep it on me just in case there's somebody in my server that like or my Discord server that's like, hey, I forgot trig. It's like this is the book to reference. So and yeah, so it's more. This is more of the ideal high school book that you would want to complete to move on to more advanced books like Apostles' Calculus 1 and 2. You want to complete both of these very thoroughly, and you'll find that a lot of the things that you do in real analysis get kind of covered here. There's even like measurable spaces. And integration is actually handled first in these books because that's historically accurate and it's also more leverageable conceptually. So these two books are extremely important, and it even has differential equations, linear algebra, um, you know, sequences, series, multivariable calculus, and then it'll also get into vector analysis, and at the end, probability. So the probability section is really good as well. So make sure that you really take advantage of like reading through these very carefully. I haven't actually completed them, but I've read through both like all of them. I just haven't like completed like most of the problems or whatever. But still, like it's kind of like a history book as well. So I'm just gonna keep glazing the calculus. You need to get the calculus done, and then linear algebra. You're going to want to work through all these chapters for this nice abstract treatment of vector spaces. So we have two American mathematicians, and then we have this Soviet mathematician here as well. That just gives us the more abstract treatment of our introduction to bilinear forms and spectral theory. So these exercises you really want to pay attention to, and I've gone through quite a bit of them, but I'm still working my way. Um, and then yeah, so and I would say where I rank on here is I'm like just about to leave the base camp. Um, and well, I've left the base camp and I'm kind of playing around with stuff over here, if that makes any sense. But I haven't like fully explored everything that we're gonna do. But that's kind of where I'm at. So a lot of this is also a kind of a to-do list for me as well. I'm gonna probably have read all of these books by some point in my life. So yeah, but yeah, I've read these two as well. These are very good books. You want to complete both of these and derive really all of the key results, like the Lagrangians, Hamiltonians, Noether theorem, and then electromagnetic fields, relativistic invariance. And you really need to, when you go through these two, you need to emphasize the idea of like physical reasoning. So I have this really general, action principle, right? That gives me a set of differential equations over some configuration space. And I'm like, okay, well, now that I have this really general type of thing, I need to start imposing these conservation laws or these assumptions that allow me to simplify, do really like, slick types of manipulations. So there's a lot of tricks in physics that a lot of the pure mathematicians are incapable of until they actually do physics. So that's really important to realize is the importance of starting with good mathematical training and then going into physics and really struggling with it. So yeah, you want to rederive a lot of these mechanics and field problems. You also want to make up your own problems for these as well, because physics is something that just keeps continuously um, having really interesting theoretical results even in mechanics and classical field theory. So yeah, so for the pure mathematics route, you basically have your real analysis here or advanced calculus. This replaces real analysis. This I would say advanced calculus with Sternberg and Lewis and calculus 1 and 2 from Apostle, they replace real analysis. Um, just because after you've mastered the base camp, um, really you're gonna connect analysis to geometry, and these abstractions from these later books are gonna come from these types of physical motivations like symmetries, invariants, forms, and then you'll prepare basically for nice, topological structures that emerge out of everything. But yeah, so that's basically. I mean, it is. You might think like, well, that's applied. It's like, no, no, no. It's pure mathematics. It's just you kind of have the superpower of physics on your side with pure mathematics. Okay, so yeah, so you'll have this. I mean, manifolds get covered in Sternberg, differential calculus, integration, Banach spaces. So everything that you would normally get that. Also, exterior algebras, Stokes theorem and abstract settings, nice geometric tools. Everything is here, so it replaces a lot of the other books. You'll get a treatment of holomorphic functions with Alforce, Cauchy's theorems, residues, conformal mappings, Riemann surfaces, and it emphasizes connections to real analysis as well. Like, so it's pretty good. Analytic functions, also some uh, what's it called? Some confluent differential equations. I mean, this book, it has a lot in it, and it's. I mean, I also have it right here. It's just give you the yeah. So it's like 300-ish pages. It's literally 300 like 17-ish pages, and it's pretty good. I enjoyed going through this one, and then there's also linear algebra and geometry. Um, this is more of like more of a geometric approach to linear algebra, and it's kind of not really a linear algebra book. It's more of it just has some nice. This would be more of an applied book, I would say, because it has nice applications of physics, quadratic forms, but it also talks about projective geometry, multilinear algebra. So it just kind of strengthens the geometric perspective alongside the analysis text. So that kind of is a nice foundation here, which gives you complex real and just like how to connect it. Now, you'll probably want to revisit the Basecamp after completing these as a pure mathematician and really try to like play around with what you've learned here and relate it to some of the systems that you've played around with in these other texts as well at Basecamp. And that's just good. It's just good habits to continuously revise your basics, right? Now, Lang's algebra. This is your pure mathematicians, like I guess encyclopedia of like groups, rings, fields, modules, Galois theory, homological algebra, just the basics of it, like an introduction. So you'll just have like a nice geometric intuition from Manin, and analysis from these ideas, and I think this is a good stepping point to prepare for number theory and geometry, and things that appear in physics as well, like Lie groups and the symmetries from mechanics. So, anyways, and fields. So then, I would say from here you can either go if you think physics is interesting and you want to learn more about like fields. There's a course for mathematicians, so that's very interesting. But really, you're going to want to next develop, or really, you can do either one. You can develop topology first, and then algebra. It's good to really kind of train these things in parallel with each other, um, because there's a lot of results in quantum field theory that just make pure mathematics a lot more easier and digestible if you just kind of go through the motions with this course here. But you're going to want to develop formally develop topology with groupoids, covering spaces, fundamental groupoids, and like higher categorical views of the subject. So you're going to be simultaneously developing all of those things, but it gives you a nice flexible approach for bridging point set topology with algebraic topology. And then speaking of all of that, you might find differential forms in algebraic topology, another interesting book. It introduces de Rham cohomology, some homotopy theory towards the end. So yeah, this is a pretty good one as well. But then once you've done played around with these books and completed maybe one of them, then you could probably move on to algebraic geometry. And this mathematical kind of treatment, I'd say you really want to get this one in, because this mathematical treatment of like the perspectives of quantum field theory and string supersymmetry, you're going to use this to formalize like the physical structures of fields, to then get like invariance, and these algebraic structures in Hartshorne's differential, or sorry, algebraic geometry. So you'll get schemes, cohomology, algebraic varieties, and this really builds on Lang's algebra and just prior physics. And then you will have modern number theory by Manin. So this gives you a nice view of zeta functions. It's all about zeta functions, class field theory, Diophantine geometry. So just skimming the table of contents here, really like it connects algebraic geometry by using the tools um, previously that we've established in both of these two books of Lunis, and some of the zeta functions that were introduced here, and it just gives you this algebraic geometric perspective. So this would be a nice thing to supplement for the pure mathematical side of things. And then you'll want to go on to cohomology and differential forms. This one goes really deep into de Rham cohomology, sheaf cohomology, and connections to geometry, and developing the idea of physical invariance. And then you'll get homotopy, homology, spectra, explained in this nice little 200 page book, 200, 300 page-ish book. And then the last thing I just kind of put here for fun, this is one of my like reach books that I want to get to, which is essentially stable homotopy and equivariant methods to solve specific problems. So this is like a nice elite level engagement with homotopy theory and invariance, which I thought was pretty interesting when I formally have read through this one completely. I haven't worked every problem, but homotopy theory is pretty darn cool for describing like spectral sequences and all of these things. So that's pretty cool. Now we can move on to engineering and physics. Now, how to think about this is you're going to want to master manifolds. As a physicist, that's probably the first thing you need to do. It's just master manifolds, bundles, connections, curvature, and Riemannian geometry immediately after classical theory of fields. Just because you're going to need that language. And then, of course, you're going to want to develop de Rham cohomology after you've developed the exterior forms, and all of those things get introduced by Sternberg here. So you kind of want to just like speed run through those things. Characteristic classes, topological invariance, all of these things get explained in Bott and Two's algebraic topology. having a mesh or being able to algebraically count, um, and enumerate the smooth manifolds, with like cochains and seated complexes, so check complexes as well. So all of those things are in here. You also get Pointryagin classes, Chern classes. So everything from these two books really are kind of like a nice speed run after Landau and Lifshitz, or you could read them all together. Um, physics, I mean, there's physics is the most messy kind of subject because it's exploring both weird phenomena in the real world, but also in abstract mathematics. But yeah, these are both pretty good. And it connects classical fields to prepare yourself for gauge theory. Um, yeah. So what's next? Quantum mechanics. The non-relativistic and the relativistic quantum mechanics. Um, Basically, you're just going to derive quantum principles, perturbation theory, and then extend it to relativistic types of things. You want to think about physical reasoning in these books. I'm actually still reading quantum mechanics because it's really long, and I've briefly skimmed this one for like looking at analytical continuation, um, for like scattering poles and all of these things. But yeah, like I've only referenced these books pretty much. I'm really formally going through this one. I actually started like 2 days ago, but I'm pretty. I'm getting through it. It's a good book. Like, don't get me wrong, but I'll have to like read it very carefully. This one's one of the hardest ones for sure. Um, Q QFT or sorry, quantum electrodynamics isn't really that bad. I think it's just this one. It's a lot of stuff to think about in this book. But yeah, and then also I have Lando's lectures in nuclear theory as well, just because it covers nuclear models a little bit more in depth than this quantum mechanics text does. It goes, goes into nuclear magic numbers and like more phenomenological aspects and interactions that happen with the nucleus. So yeah, that's kind of where I was thinking. And then you'd want to move on to Riemann surfaces. So Riemann surfaces, um, I would say actually, yeah. I would say Riemann surfaces, they kind of give you your complex analytic and geometric types of structures that allow you to have like these conformal methods and moduli in physics. So I would say you don't really, I mean, you can do Lars Alford. I mean, you can just kind of skim this with his Riemann surfaces book after you've gone through the scattering phenomena and like, your S matrix and like all of those things that demand like a lot of complex analytic types of manipulation and physical reasoning. But all of those things kind of come naturally. So that's why I put Riemann surfaces next. And then I would say maybe gauge fields and Cartan Erasmon connections by Hermann. So this really starts to talk about gauge theories and by the idea of like principal bundles, Erasmon connections. So this one also could be supplemented as well with the differential geometry by Sternberg. It just depends like what route you want to go. Again, physics is messy, but you're going to want a nice rigorous treatment of gauge theories, and it's also interdisciplinary mathematics. So Hermann has also like gone for like more computational science types of books as well. So he was an American like pure mathematician, but he also did all of that. So yeah, pretty neat. And yeah, so you bridge differential geometry with the idea of physical gauge fields themselves, and then we get Einstein manifolds. So Einstein manifolds by Bessey, basically you study really in depth the like Riemannian manifolds and on Einstein metrics, spaces of metrics, curvature, geometric types of quantities that are relevant to general relativity and beyond. So that's kind of the premise of this book. This is more of an aspirational book for me. And then microlocal analysis of quantum fields and curved spacetimes. So this is basically like a book like that does QFT. It attempts to do QFT on like curved backgrounds instead of flat Minkowski space. So you'll do like wavefront sets, microlocal techniques, you know, and this connects to Sternberg's geometry as well, because you'll have to, and also Garage, his videos are all online, so he has like some lectures and stuff that are pretty good. And then I would say you have the rest of these Landau Lifshitz books. I've read through them pretty non-linearly, and I haven't even opened continuous media yet, but I think I probably should. Um, but the rest I have, basically, I mean, this is just they're just engineering applications because you have in statistical physics like the foundations of ensembles, fluctuations, and phase transitions for all these different routes. And then, fluid mechanics, elasticity. This is basically continuum mechanics as a field now, more modern. It's called continuum mechanics. And then you would have like continuum electrodynamics, theory of like radiative transfer, um, electromagnetism propagating in just media, and then you'll have the more advanced kinds of applications for statistical physics, statistical phenomena like the quantum Hall effect or Kerr magneto-optical Kerr effects. Well, that would be more continuum electrodynamics, but yeah. So you'll get these really more advanced types of things, and then to bridge all of it together, basically the final volume, the physical kinetics. You're basically like you're completing a unified type of like idea of non-equilibrium physics, multi-scale phenomena, and it's just engineering across like transport types of phenomena as well. So yeah, it's not really one field, kinetics. It's more like it bridges mechanics, fields, continua, all together. So these are more like the engineering base books, but I'm having to go through and complete these as well. So yeah, that's everything for physics. And now the next thing, if you want to look at more financial applications or those types of things, you want a good background in probability. So I added a bunch of books here. I think a good stepping stone into um, really thinking about the probability and stochastics, uh, wealth preservation type processes, or for being able to understand those things, you have to first have some good measure theoretic probability, understand martingales, and you're going to want to relate it back. You're going to want to relate martingales back with conservation laws. So I would also recommend quantum mechanics and statistical physics as well, as supplementary to thinking about probability, because probability basically just gets developed completely in quantum mechanics. So it's kind of a side quest. And then you'll have a reference as well for stochastic differential equations. So this one just gives you a good treatment of what a stochastic differential equation is, of diffusions, and the applications to modeling itself. So these are the two market books that I think aren't like trash, but are like actually kind of good. So Bouchard here and Mark Hotters, they wrote this theory of financial risk and derivative pricing. It's not really a theory book. It's pretty applied. So if you look through it, it applies statistical physics to risk management, fat tails, other things, pricing, right? And it gives you a bunch of laws. It's matrix models, random matrix theory. Just really, really good book. And then for more of the high frequency guys, the trade quoted prices by Bouchard as well. You have, he talks about microstructure, order flow, latent liquidity fields, empirical high frequency dynamics. So the empirical laws that kind of come out or that have been observed, as well as just price formation. So how the market chooses to form price, like at a less coarse grained, kind of like noisy, fast time variable type of scale. You also get the mathematical theory of Bayesian statistics. So this one has like neural networks and all kinds of stuff in it. So this is a really good supplement, I would say, to read. all together for more finance applications. But yeah, so singular learning theory, model selection. So basically, I mean, this is just data science. I mean, finance is really just data science and kind of a. I mean, this would be very closely related to multiphysics and kinetics. So because it's diffusion processes. But yeah, and then geometric. Uh, I would assume if you wanted to have like a theoretical type of understanding of financial markets, I would read Suriao. Um, he's French, but I don't know. It's like Suriao. I don't know how to say that, bro. But yeah, uh, he talks about geometry, momentum maps, from more constructing things from a statistical point of view as well. So this would be a good bridge to finance as well. I would say this book is pretty it'd be a hidden gem for sure. So and the structure of dynamical systems is pretty important because I would say two of the most highly leverageable uh, methods of computation would be finite element exterior calculus and geometric numerical integration. Just the classes of structure preserving algorithms here. Why I think these are important is because you have some um, symplectic update laws or volume preservation, Lie group integrators. All of these are going to preserve invariance in simulations. And really, there's a lot of hidden invariants that are talked about in here in these books. And and then it shows you exactly how to theoretically handle them. So this would be more of like the engineering or the let's write some software that we can actually deploy on some high frequency algorithm or whatever. And then finite exterior calculus. This is discretization schemes using differential forms. So this is very, very powerful for partial differential equations in pricing, risk, or market models. This also really connects to the algebraic means of having these more finite approximations or meshes or CW complexes for counting over them to give you like the actual manifolds and smooth manifolds themselves. So the finite exterior calculus is pretty. It's a nice thing to keep in mind as well. Um, Generalized functions. We This is like good for Fourier analysis, distributions for signal processing, filtering, um, volatility modeling. You would need these are more kind of advanced analysis tools, but this introduces the concept of like nuclear spaces, of like Schwartz types of spaces, and you just have to know like why those things are important. But they kind of replace the general um, kind of like stochastic formalization to more of like generalized functions and distribution theory. So uh, generalized functions in general would be a good thing for quants to look at uh, for like fluctuating like Gaussian type fields. And then you also have Chern-Simons theory. Yes, Simons as in like the Rentek Simons. Matrix models. It kind of talks about matrix models as well. I think matrix models were mentioned here, so that's another reason why I included it, not just for the name, but also for like some of the you know uh, some of the things that are mentioned in this book. And yeah, just advanced invariance um, with these exact methods that are applicable to some more quantum inspired finance or complex system modeling. So, but yeah, because quantum finance is a new thing as well. Like we have like a bunch of quantum computing type scientists that are working for banks and stuff. So I also have that. Yeah, that's everything. So here's another picture of Olympus Mons. Another look at it. I think it's pretty cool. So if you want to hike Olympus Mons, then you'll read everything. But if you want to, you can get to the top of Mount Everest probably, by any of these routes or whatever. So yeah, thank you guys for watching. Hopefully this was better than my last Mount Everest video. My last Mount Everest video was, I mean, it was all right, but I think this one is much better. I kind of just based everything off of the kind people that made these that made these books here, or these book lists here, and I just kind of forked it and made this path for myself, and also hopefully you guys like get something out of these two books. If you're, I mean, and I added a couple of things, but for the most part, this is all the work of Mischification and the Portal reading lists. So yeah, that's all I'm doing is just relaying you guys to resources and having one place that nice video reference so that if you guys keep asking me questions like what book should I whatever, like this is the direct path. All right. So thank you for watching and see you guys next time.